Hi, good afternoon, everyone. Welcome to the talk, New Compat Vulnerabilities in Linux Device Drivers. This is a 25 minutes talk, so just ignore the schedule outside. My name is Chen Fu, and that is my colleague Peng Fei. We are security researcher and developers at Baidu XLab. We have been focused on mobile IoT and Linux kernel security. Our major work is developing security solutions for Baidu's AI platforms. Besides that, we also do some security researches, including finding vulnerabilities in Linux kernel and device drivers. In last year, Peng Fei and I got more than 30 Linux kernel and device driver CVEs. This is our agenda. First, we will introduce the concept of Compat and the security risks of Compat. Then, we will introduce some Compat vulnerabilities found in the past few years. And we will introduce how we found a new type of Compat vulnerabilities in Linux device drivers. After that, we will give some advices and mitigations to developers and security researchers. At last, we will have some conclusions. Okay, let's start. Compat is the 32-bit compatibility mode in 64-bit Linux kernels. On a 64-bit Linux system, when the 32-bit user space program makes a system call, the Compat version of the system call entry is used instead of the original 64-bit system call entry. In general, the reason that Linux kernel use Compat mode system call is to handle the differences in the data sizes. As we know, many system calls have parameters with different sizes in 32-bit and 64-bit system. For example, a structure parameter in a syscall may have a pointer type or a long type field in it. Their size are platform dependent. So, when the 32-bit user space program makes a system call and passes parameters into kernel, Compat mode system call will first convert the values of these parameters into corresponding 64-bit values. This is an example of set time of day syscall. On the left side, there is the 64-bit system call. On the right side, there is the Compat mode system call. We can see on the left that the user time value structure is directly copied into kernel time value structure using copy from user. And on the right, we can see that the type of user parameter, which is Compat time value, and the kernel structure, which is time value, they are different. So the Compat version uses a function called Compat get time value to convert user Compat time value structure to kernel time value structure. Also, from this case, we can notice that there are duplicate codes in these two functions. We can see that this part of codes are the same. So from this example, we can notice some potential security risks of Compat code. The first security risk is code redundancy. Actually, code redundancy is common in many Compat mode system call implementations in Linux kernel, which means two similar copies of code and data structures need to be maintained. With no doubt, these maintenance efforts introduce more security risks. And furthermore, compared to original 64-bit system calls, their Compat counterparts usually have some additional definition of data structures and additional type conversion and additional data processing logic, which expose new attack surfaces to user mode processes. In the past few years, there are some, but not too many Compat vulnerabilities has been discovered. Almost all of them are found in device drivers. We think there are two reasons. First, compared to the number of system calls, the number of device drivers are much more. And secondly, device drivers usually have to handle more complex data structures than normal system calls. And the most common root cause of these vulnerabilities is the inconsistency between compat and non-compat mode. There are two types of inconsistency. The first is the inconsistency of data structure definition. And the second one is the inconsistency of user input validation logic. Let's see some examples. This is an example of inconsistency of data structure definition. In this case, the left one, MDP layer commit v132 is the 32-bit user space data structure, while the right one, MDP commit v1, is the corresponding 64-bit kernel space structure. The two structures have almost the same definition, making it seems easy to convert. However, the array field, we can see that array field reserved in these two structures have different size. They should have been the same, but developer made a mistake. So the one in the left is larger than the one in the right. And then when kernel calls memcopy to copy data from the larger one to the smaller one, there's a stack overflow. And in this case, we can see the inconsistency of user input validation logic. This function EEP-ROM init config32 is the compat mode version of function EEP-ROM init config, which is not shown in this code snippet. And the EEP-ROM init config function correctly validates user input. Well, we can see that this compat mode version does not validate, which leads to heap overflow. So the patch, we can see that is simply adding validation logic on it. And in this case, a function called isCompat_task is used to implement both compat and non-compat logic in one function. This can reduce some code redundancy, but still can't eliminate the inconsistency. So in this function, when implementing compat logic, the developer forgets to validate the user space pointer, power setting iter, and its size sets down, which leads to out-of-bounds array access. Based on our research on those past compat vulnerabilities, we found that the past research on compat vulnerabilities only focuses on normal program logic. So these vulnerabilities look just like any other vulnerabilities in any other part of the kernel. Seems nothing special. But during the research on those vulnerabilities, we went deep into many device drivers code, and we found that in device drivers, compat and non-compat codes are usually mixed together, making the whole program logic very complex, even confusing. So we came up with a question: can these mixed codes cause some unexpected program logic, even causing some security problems? Then my colleague Pengfei will introduce our research and finding.
Hello, I'm Pengfei Ding. Let's continue. As we know, out control is the most commonly used interface in device drivers. So our research mainly focused on out control. This is a simple out control flowchart in device drivers. As we know, out control have three parameters. The first is file descriptor. The second parameter command is the device-dependent request code. The third parameter is a pointer to user memory. Usually, it points to a structure. The structure type depends on specific device drivers and commands. When 64-bit process invokes out control, it passes 64-bit version of parameters to kernel. Then kernel will invoke unlocked out control with this 64-bit version of user parameters. When 32-bit process invokes out control, it passes 32-bit version of parameters to kernel. Kernel will invoke Compat out control instead. In device drivers, we define 3 kinds of out control command parameters. Command 32 are used by only 32-bit programs. Command 64 are used by only 64-bit programs. And some common commands can be used by both 32-bit and 64-bit programs because their corresponding data structures, the third out control parameters, are the same on 32-bit and 64-bit platforms. After analyzing many different device drivers code, we summarized this typical detailed flowchart of out control in device driver implementations. In most device drivers, no matter Compat or non-Compat mode, their functionality are the same. So Compat out control and unlocked out control both count some common codes to implement their some functionality. And the most important difference between Compat out control and unlocked out control is Compat out control has one extra step. It needs to convert 32-bit version of the parameters to 64-bit version. Compat out control will make a conversion according to the value of command 32. So we had a fresh idea. What if we intentionally confuse Compat out control parameters with the unlocked out control parameters? Will it affect the behavior of the conversion, thus causing security problems? Then we listed the following 6 conditions with confused parameters and tried to verify whether they have a security problem. First, we found unlocked out control does not have conversion behavior. In number 4 and number 5, when you pass a command 32 to unlocked out control, it will be filtered. So number 4 and number 5 are ruled out. Second, in number 6, when you pass a pstruct 32 with a command 64, out control call will return fail directly because the size of structure pointed by pstruct 32 is less than what kernel needs. So number 6 is ruled out. At last, processing logic of pstruct parameter in out control depends on the value of command. So we ignored the variable pstruct, only focusing on how changes of the second parameter command will affect out control. So number 3 is equivalent to Compat out control with command 32 and pstruct 32 parameters, which is the normal case. So we just needed to focus on the safety of Compat out control with 64-bit command. Then we analyze the many device drivers, try to find what behavior will be triggered if we pass command 64 and carefully constructed malicious p-struct parameters. In some of them, we found when command 64 is passed to Compat out control as its second parameter, the check and conversion will be bypassed. Then, with carefully constructed malicious p-structure parameters in some of common codes, we managed to trigger kernel vulnerabilities. So we wanted to discover more vulnerability by fuzzing. Existing Linux syscall fuzzing tools, including Trinity and syscaller, do not support Compat. So we added Compat support on Trinity and syscaller, then use them to fuzz the device driver. As expected, we discovered more vulnerabilities. Here I summarize 4 security issues that can caused by this type of Compat vulnerabilities. Since this logic vulnerability causes check and conversion on user input being bypassed, malicious user input could cause several security problems depending on behaviors being bypassed. Bypassing verification on user input array lengths can lead to out-of-bounds read and write to this array, thus causing privilege escalation. Bypassing verification on user input pointer value can lead to arbitrary memory read, thus causing information leakage. Compat alloc user space is used to allocate user space memory in kernel. Malloc is used instead of it for check and conversion, which can increase the operations on kernel memory, thus increasing the security risk when check and conversion is bypassed. Using is Compat task in common codes to deal with Compat mode and 64-bit mode, it is easy to cause logic confusion. Ignoring the security audit of the Compat code in common code, and it is more likely to cause security problems when bypassing check and conversion. Here, I list 2 CVE we found to further illustrate this vulnerability type. In the left diagram, the second step processes the 32-bit command, including check and convert user input. If we pass directly its corresponding 64-bit command, the validant of user space pointer checked by copy from user will be bypassed. So it can be assigned to any value by user, resulting in arbitrary address access when using memcopy. This is the second example. In the left diagram, the second step processes the 32-bit command. Copy from user checks user space pointer. If we pass directly to its corresponding 64-bit command, the validation will be bypassed. This pointer can be assigned to any value, resulting in arbitrary address access when it is dereferenced in the third step. Here, we summarize the 3 tips to mitigate the Compat vulnerability. Try to use Compat alloc user space instead of camalloc during entire user input check and conversion. Avoiding security problems caused by direct operation on kernel memory. Try to avoid using its Compat task in common codes to deal with Compat code and 64-bit mode, which may cause logic confusion and security problems. We can use Compat alloc user space to help convert user parameters from Compat mode to 64-bit mode. Then proceed in common code so as to avoid using its Compat task. Try to use struct instead of pointer in user input to minimize validation of user input, trading space for efficiency and security. This is our 3 advices. Development and test engineers should strengthen the testing and auditing of Compat code. Bug tools and code auditing tools should give more attention to Compat code. Security researchers can continue to explore Compat attack on more platforms. Through this speech, I hope to help you understand the concept and security risks of Compat, as well as some Compat vulnerabilities in the past. More important, we identified a new type of Compat vulnerabilities in Linux device drivers, which had not been discovered by any others before. At last, I wanted to show you how to discover this kind of vulnerabilities and how to avoid them in development. Thank you. Any questions? Okay.